All right, well, welcome back. So in this section, we're actually going to look at a pretty cute and old result that's actually due to Fermat about the ability to actually decompose certain primes into a sum of squares. So it feels a little kind of off the beaten path and that it's not actually going to have, immediate applications in some of these crypto problems, but it actually does have a really nice argument that's actually going to make use of lattices. So there are actually going to be multiple ways to go about showing this particular result. It's a very old and famous result. So there's a ton of different approaches out there. I'm going to lean on the one that makes use of lattices just because that's where we've been playing for a little bit. So it's nice to see some of these old, adorable number theory results kind of percolate back up just to kind of remind us that numbers are also super duper awesome. Even though we've been playing in lattices and crypto systems, we can still kind of lean back on some nice little number theory results as well. So we're going to chat about kind of the overall statement, and then at the end of it, we will, well, in the middle of it, we'll then show it with some lattices, and then towards the end, we'll actually go back and chat about some efficient algorithms to actually do this decomposition. So the goal is going to be a sum of squares, and we're going to connect them to lattices. So I have this nice little picture of like, how does this connection actually be formed? But before we actually go ahead and state the official result, I want to do a little bit of exploration, I guess. So the initial question is going to say, which primes can be written as a sum of two squares? So down below, I'm going to have some primes up to about 47-ish or so. So I've somewhat spoiled the surprise already because I've decomposed some of them and then not decomposed the others. So I'm claiming that the ones that have the little red X's next to them can't be actually decomposed. And then the ones that are actually decomposed have a little check mark and they actually do work. So we'll make sure that it actually is what it claims to be. So we're just going to run through this little list. So I have 2, which can obviously be decomposed as a sum of 2 squares because it's just 1 plus 1 and 1 is just 1 squared. 5 can be decomposed as a sum of 2 squares because it is 1 and 4 added together, namely a 1 squared and a 2 squared. You can see that anytime we add 1 to a perfect square, it's obviously going to be decomposed as a sum of 2 squares. So that type of phenomenon happens at 17, and it also happens at 37 as well. So 37 is 36 plus 1, 17 is 16 plus 1. But we also get a few other interesting decompositions as well. So 13 was 4 and 9, or 2 squared and 3 squared. 29 is then 4 and 25 because it's 2 squared and 5 squared. And then lastly, I'm going to have 41, which is 16 plus 25, or 4 squared plus 5 squared. So those ones are great because they do in fact all work. I colored those all in green and I colored the 2-1 in blue because it's going to be a little bit of an outlier just because 2 is an even prime and it just breaks things all around. So 2 is going to get kind of shoved into its own bin. The green things are all going to be in their own bin. And then the exploration is going to be what's happening with these red ones. Why am I claiming that the red ones don't work? Well, if you look at 3, there's only a couple different ways you can add up integers to actually give you a 3. So I should be dealing with positive or at least non-negative integers here. So I'm going to see, well, a 3 can be a 0 and 3. That's not a sum of squares. Or it can be a 1 and a 2. Well, that's also not a sum of squares because 2 is not a perfect square. It's the square root of 2 squared, but I want that base element to actually be an integer. So that's part of the reason why we do in fact have that big old red X hanging out on 3. You can run the same game on 7. There's only a handful of ways to actually add up to 7. So 0 and 7, nope. 1 and 6, nope. 2 and 5, nope. 3 and 4, half good because the 4 is a perfect square, but the 3 isn't. So that's why we get a big red X there as well. If you wanted to, you could run it on 11 as well. So 0 and 11, no. 1 and 10, no. 2 and 9, half there. 3 and 8, 4 and 7, I guess. And if you go on down the list, you're going to see that it's not going to work as well. It should be easier to make those pairs than it is, but as I'm doing in the head, I'm like, okay, I got to go to the next number and make sure I can do the subtraction work. So I'm just going to claim that it won't work after that as well. If you go to 19, 23, and 31, and 43, and 47, all of those are going to break as well. So it's, this unfortunate collection that some things work, other things do not work. Before we spoil the surprise of lumping those together, I'm going to jump into a little bit of code just to, I guess, showcase that we can do this super duper inefficiently, and then at least maybe segue into which ones work and which ones don't work, and then properly state Fermat's actual results. So I'm going to swap screens into some CoCalc Sage land. So up on top, I have this very, very inefficient function that's called sum of squares. It's going to eat a p, which I'm just hoping you're feeding it a prime. And then what it's going to do is it's going to do this process of trying to find these sum of squares. Maybe you can kind of think about that as a process in 13, is that if you eat 13, you can start subtracting off perfect squares and then hope that the output is going to be a perfect square. So 13 minus 0, 13, not a square. 13 minus 1 is 12, not a square. 13 minus 4, well, that's going to kick out 9, which is a perfect square. So that's where we're going to then return what those two little bases happen to be. So that's what this little super duper inefficient process is running. It's going to eat that prime, p, and then it's going to cycle from 0 up to essentially the square root of that prime. And then it's going to store those numbers as x's. It's going to compute y2, which is like y squared, by evaluating p minus x squared. If that little result is a square, then it's going to return back to the user those two little entries. So if I ran this little sum of squares on the number 13, you'll see that it'll return that little ordered pair of 2 and 3. So then I'm just going to have this big old loop that's going to like run through the primes up to 100, and then a few little fancy just making the printout statements look nicer. So it's going to return back a pair x and y if it does work. If I make it through this entire loop and I don't find those magic little pairs, then it's going to return false. Well, it's going to return as like an ordered pair, false comma false. So if it does work, I'm going to print out, well, what that prime is, and then it's going to be its decomposition into a sum of squares. Otherwise, it's just going to put that big old x next to it. So if I turn that on, voila, you can see some of that list that I had before. I think I hand wrote those portions of things. So then if you wanted to keep on going, 53 will work. You also see that 61 will, 73 will, 89 and 97, and then the other ones will not. So our goal here then is to stare at this big list and try to find patterns between which ones worked and which ones did not work. And as I alluded to before, let's pretend that that 2-1 is not part of the mix and just look at those things down below. So if you stare at that long enough, you may or may not see some pattern emerging. They're all odd numbers, obviously, because they're all prime. And sometimes we like to further classify odds not in a division by 2 structure, but rather in a division by 4 structure. So what I mean by that is if you have any odd number, it's essentially either going to be a 1 or a 3 modulo 4. So if you have a number and you divide it by 4, you have essentially 4 possibilities for remainders. You have 0, 1, 2, and 3. Well, if you're a 0 mod 4, you're divisible by 4, which means you're not prime. And if you're a 2 mod 4, I almost like flicked you off because there was my 2-1 in there. So if I'm a 2 mod 4, well, that means that I'm for sure going to be even because I'm some multiple of 4 plus a 2 afterwards, which would mean that I'm even and, well, not prime as long as I'm not including 2. So if you look at numbers modulo 4, and in particular, you look at primes modulo 4, they're going to be a 1 or a 3. And if you look at these ones that have little x's next to them, they are all of those ones that are going to be a 3 modulo 4. You can actually see it right off the bat. So 3 is 3 mod 4. 7, well, it's 4 more than 3, so it's 3 mod 4. Same with 11. That's a 3 mod 4. If I add another 4, I'd actually go up to 15, which is not prime. And then if I go up again, I'm up to 19, which gets an X, then a 23, which gets an X. And then I'm going to jump over another non-prime thing and then jump again, which is going to bring me up to 31, which again is a 3 mod 4. And if you keep on going down this, you'll see that all those little X's correspond to primes that are in fact 3 mod 4. Where all of the ones that do in fact have a decomposition are all a 1 mod 4. So 5 is a 1 mod 4. 13 is 12 plus 1, so it's a 1 mod 4. 17 is 16 plus 1, so it's a 1 mod 4. and on down that little list. So that's the official statement due to Fermat, which is going to say that if you have one of these primes, if it's a 1 mod 4, then we'll have this decomposition as a sum of two squares. And it's actually an if and only if statement. So those two things go hand in hand. We'll chat about how that process is actually going to go in terms of showing that result. That's where the lattices are going to come into play. And then later, we'll actually chat about more efficient ways of doing this, because this is complete trash, because it's going to have to cycle from 0 up to the square root of whatever prime you're going to feed into that thing. So if you give it any type of interesting prime, it's going to crash and burn. So we will have a much more efficient process that will appear a little bit later, and you'll have a chance to run through some of those arguments as well. So I'm going to jump back into the notes. I'll hit pause here so that we can resituate ourselves, and then we'll at least show the forward direction, come back to the reverse direction, and then seal up a few things as well. So I'll hit pause and swap.